Good morning, fellow biologists. This is Mr. Ebb coming to you about lesson ED-1, designer planes. So let me tell you what we did with the designer plane activity. Each student was given a sheet of paper, 8.5 by 11 white sheet of paper, and they were given two rules. One, you have to use the whole sheet of paper. Two, you cannot just crumple it into a ball. So you have to use the whole sheet of paper. You cannot crumple it into a ball. And they were asked to create an airplane, thus designer planes, to fold this piece of paper into an airplane. Some of you have lots of experience at making airplanes. Some of you may have never made a paper airplane. That's okay. Do the best you can. So I need to take this and convert it into something like this. And so students took and created a plane. And then we went into the cafeteria and we all lined up and we were about to throw our plane when I stopped the group and asked them, how are we going to tell which plane does the best? And people threw out the ideas such as which plane goes the farthest distance, which plane stays in the air the longest, which plane goes the fastest. Those types of criteria were briefly talked about, and we decided that the best criteria and the easiest one for us to monitor was which plane goes the furthest. So people lined up, 1, 2, 3, fly. And we noted whose planes went the furthest and whose planes didn't go so far. And then we came back into the classroom. When we came back into the classroom, I'm going to share my screen here for a moment. We went to our document and we noted in this box and we described what our plane did. Our plane flew for approximately 20 feet in the air and then landed on the ground. Our plane instantly went to my feet and hit the floor, whatever it was your plane did. Then students were asked to make a modification to that plane. So now that we knew the criteria, when they first made the plane, students didn't know what the criteria they were going to be measured on. So the advantage now is you've tested your plane once and you now know what criteria you're being measured on, which is distance traveled. You need to make at least one modification or change to your plane. Stop sharing for a second. I provided 2 different size paper clips. I provided just regular old Scotch tape, and I provided some staplers. Students could use any of those materials. They didn't have to use those materials, but they had to make a change. Some students added paper clips, some students added staples, some students taped, some students refolded, but they still, 1, had to use a whole sheet of paper, 2, could not just crumple it into a ball. So after they did this, we went back into the cafeteria to fly our plane again to see if our changes made any difference. But before we started, I said, well, how many times did we do the trial the first time? And everybody said, just once. And my question was, is it fair to do a trial just one time? And most people quickly said no. Too many things could have happened that were just due to chance. Too many errors could have happened. You could have just had a bad release. You could have bumped into somebody when you released it. So you need to do trials multiple times. The more trials you have, the less likely there's any problems due to error or chance. So ideally, we do this 50 to 100 times, but we also have to be real about time frame. So we decided we would fly the planes 3 times with our modifications. So we returned to the cafeteria. We did our planes 3 different trials. And after 3 trials, it was very clear who had the top 3 or 4 performing planes. And it was very clear who had planes that just didn't perform at all. Both valid results. The group that had the best planes, they had some strategies and techniques that we probably want to pay attention to. The groups that had failure, that's okay, because now you can start learning on the things you want to avoid or not do. So we came back into the room and we went back to the document, excuse me, and we recorded what our plane did the second time. Let me back up because I forgot one step in there. Actually, before we went back into the cafeteria, we made some hypotheses. So this is usually new to 9th graders, the null hypothesis versus the alternative hypothesis. The null hypothesis is really the main hypothesis that's used in real research. And scientists are actually trying to prove the null hypothesis wrong. Because if you can't prove the null hypothesis wrong, then your research question probably isn't valid. So the null hypothesis states that what you are testing will have no effect. So say I decided to put a paper clip on the front of the plane because I thought that would give it some more weight. Well, my null hypothesis would be if you add a paper clip to the front of the plane, it will not change the distance it flies. So again, you're stating that there will be no benefit or no effect to this. So if you add a paper clip to the front of the plane, then there will be no increase in distance at which the plane travels. I'm trying to gather data to reject that. I want to actually see when I go test my plane that it actually does go further and I can reject the null hypothesis. If I can't gather evidence that rejects the null hypothesis, then my idea about the paper clip probably is not valid. If you can reject it, you then go to the alternative, and the alternative states the opposite. The alternative states that if you add a paper clip to the plane, then it will increase the distance the plane flies. If you add a paper clip to the plane, then it will increase the distance the plane flies. So if you do gather evidence that shows, wow, when I put the paper clip on the plane, it did travel further, you rejected null hypothesis, and now you consider your alternative hypothesis. Hopefully that makes some sense. And we'll be doing a lot more work with that in the next few days. So then we went and we did our second plane trial, and then we came back and we filled in this bottom box. Did your plane go further? Did it go about the same, or did it actually do worse? And we had people in all three categories. So if you're one of the virtual students, I'm going to ask you to actually go create the plane and go through those steps and respond on the document to what actually happened as you did your own plane process. After doing that, we came back and we discussed these items in class. So we said, how did you act upon your plane? What did you do to your plane? So let's stick with the paperclip activity. So I'm going to type in here, if I was that student, added a paper clip to the nose of the plane. And by doing this action, what were you purposely changing about the plane? I was changing the weight of the plane. And of course, you'll make answers in those boxes that fit the scenario that you chose. How did you determine your plane's response? Well, we had decided as a class that the distance traveled was going to be an indicator of whether our change in the independent variable made a difference or not. So when you added the paperclip, if it didn't go any further or it traveled less far, wow, speak English, then we can't reject our null hypothesis, and it was not a valid choice. However, if we can show the plane with the paperclip did go further, that's how we know that it made a difference. And what about your plane remained the same? What remained about the same about the plane in this particular case is the shape of the plane. I did not refold it. The size and material of the paper. We still had an 8.5 by 11 sheet of paper. And depending on your plane, maybe you didn't change the weight. There may be other things, but those remained the same. So then we talked in class as a group, and we listed some of the factors that a couple of people had. So one person, again, added a paper clip. And then when they added the paper clip, this purposely changed the weight of the plane. You could also maybe say it's changed the stability of the plane. The response in the particular hour that we did this, the plane actually traveled further. And what remained the same about the plane in this particular case, as I already said, the shape and the size of the paper. Well, yeah, we collected a couple examples from students. and we filled that in. Somebody else refolded the wings, and in their case, they were reducing the size of the wings. And the response in this particular case is it also traveled further. And some of the things that didn't change for them, the weight of the plane did not change for them, the size of the paper did not change for them. And so we collected a couple of student examples just to give the idea, and then we had a discussion about what these different variables were. And so we talked about what is a variable. A variable, and this was the whole point of, by the way, of doing the activity with the plane, is to reintroduce these terms to you and to make sure we all were talking the same vocabulary. Odds are you've probably seen these words before, but we want to be sure that we all know these words and we all consider these words the same, because it's going to be a working vocabulary we use anytime we do lab work. So a variable is any factor in an experiment that can be changed, and you should fill this in on your own sheet that you're going to submit. And there are two major variables that are most important: the independent variable and the dependent variable. The independent variable is the variable that you are choosing to test. It's the variable that you have chosen to manipulate or change on purpose. It's the variable that you're interested in. So if you look at this, box 1 and 2 both represent the independent variable. So I'm just going to mark those as red. Those are my independent variable boxes. And so to coordinate with that, I'll mark this red down here as well. The dependent variable then is the variable you measure or observe. So how do you know if your independent variable makes a difference? You've got to have a way to know if your independent variable makes a difference. So you've got to have something you can monitor, measure, observe, so you know if the change in your independent variable was making any difference. And in our case, that was distance. We were using the dependent variable of distance traveled to judge the quality of our plane. And so that coordinates here with column 3. Column 3 represents our dependent variable. And again, we'll make that color coordinated. And then finally, all the other variables that are not your independent variable and your dependent variable, it's very important that they remain the same. They remain consistent from test group to test group, because if you have too many variables being changed, then it's very difficult to tell which variable is causing the effect. And so these are what we call our constants, which I'll mark in blue here. And these are all the variables that are kept the same between all the different groups. Right? And so those are the key parts that you'll be working with in the next assignment on the design diagrams. And we're going to start with an example of an experiment on growing corn. The last item that we talked about was the control. A control group, as it says here, is an experimental group that was not modified. You don't manipulate the independent variable here. It's used for a reference point or comparison. So in the case of the plane activity, the second time we went into the cafeteria to fly our planes, I had a plane, and I did not change my plane. I did not modify my plane. And this was a control plane, because if all of a sudden this plane was flying twice as far, or all of a sudden this plane was going half the distance it used to go, that might be an indication that something in the room conditions changed. But if this plane was going almost the same distance it went every time the first time, then I know it's not due to room conditions, it's due to the changes people made in their plane. Another example, right now we're trying to develop a COVID-19 vaccine. They're doing trials right now with COVID vaccine. And what they're going to do is they're going to give half the people the actual vaccine, and they're going to give the other half the people what we call a placebo. What looks like a vaccine, but is actually nothing more than maybe some water and salts. It has no medical properties. So the key is half the people will get the real vaccine, half the people will get the false vaccine, but they won't know who has which one, because sometimes people will psychologically report that they feel better or report that things are improving because they think they're getting a medicine. So this is how we sort of combat that. So our control group would be the group that got the placebo. Now, if the group that got the real vaccine has a 15% infection rate and the people who got the placebo have a 15% infection rate, you don't have anything that's valid. This vaccine is not worth putting out on the market. But if you have your group that got the real vaccine only has a 2% infection rate, and the group that got the placebo has a 15% infection rate, now you've got some evidence that this vaccine might be worth pursuing, that this might be something valuable. And the third scenario is you could get 15% with the vaccine and 2% with the placebo. That would be very strange, but it would mean something in your vaccine is causing people to get sick possibly. So that would be a very odd result. So that's a little bit what we mean by control. Again, hopefully that makes a little bit of sense. And then this is what we're going to introduce next, a design diagram. You're not going to fill this one in on this sheet, but this is a way to organize all of our variables. Notice we got a spot for independent variable, dependent variable, constants, and then we have a place to develop our research questions and our hypotheses. So this will come up in the ED-3 design diagrams in the next lesson. So hopefully that helps you with the designer planes, especially for those of you that were virtual and not able to participate in class. Have a great day. We'll be in touch.